I'd like to give a brief overview on the topic of hydrologic connectivity in the context of natural rivers and natural river regimes. So I'll start with the background on what I call river corridors, talk a little bit about the environmental context in which river process and form occur and how different natural regimes influence that, and then talk about connectivity. Just briefly, what is it, how do we measure it, and why is it important? So starting with that idea of a river corridor rather than a river, if you just say river, most people just think of the channel. And a river corridor is more explicitly including the active channel, the adjacent floodplain, and the underlying hyporheic zone, where the flow paths originate in the river and then flow underground for distance and return to the river. And if you think of a river, you always think of downstream movement, but in reality, of course, a river corridor has strongly three-dimensional exchanges. This diagram, coming from a paper in Water Resources Research, illustrates conceptually the exchanges of water and solids, but you could have very similar exchanges for organisms, for sediment, for organic matter. So the point is that there is strong three-dimensional connectivity within the river corridor. You can also think of that as a ternary diagram. Between the channel and floodplain, you have sediment, water, organic matter moving in both directions. Between the hyporheic and the floodplain, there's upwelling and downwelling, and then similarly between the hyporheic and the channel. So again, emphasizing that three-dimensional nature of movement down the river corridor. And because of that, of course, anything moving downstream, such as a water molecule or a grain of sediment, does not have a straight continuous path. It has long periods of rest. It may be taken completely out of the river corridor in the case of the water molecule going into groundwater or the atmosphere. In the case of sediment, it can be stored in the floodplain for thousands of years before it resumes a downstream journey. So I think of a river corridor as being composed essentially of fluxes. These are materials that come into and through the river corridor: water, discharge of sediment, and the LW here is large wood and forested catchments. Those fluxes interact with the context, and I tend to think of this at the reach scale, where reach is at least several times the average length of the active channel. That reach scale context is really governed by valley geometry. The two photos that you see on the upper right here are, on the left side of the box, a very steep, narrowly confined river valley, and on the right side, a much lower gradient river with a very wide floodplain. So valley geometry, you could specify the characteristics of it as where you are in the network, say headwaters versus lowland portions. The lateral limits, so the extent of the floodplain and the meander migration width or channel migration width. The erosional resistance of the boundaries, both the channel banks and the edges of the valley, and the stability of the base level. Do you have a dropping base level in an incising situation, or the opposite? I put human influence in here because we don't usually change the shape of valley geometry, but we do change how rivers interact with that valley through processes like flow regulation or artificial levees or channelization. So you have fluxes interacting in this context, and that results in a series of characteristics. So spatial heterogeneity, connectivity, the focus of this talk, resilience, physical and ecological integrity. Now those regimes that I mentioned early on, there are three of them that have been articulated now in the literature. The first is called the natural flow regime, first described by a paper, in a paper by Leroy Poff in 1997, and this was mostly ecologists writing this paper, and they said the integrity of river corridors and river ecosystems largely depends on the fact that they're dynamic. So there are fluctuations in inputs and boundary conditions or context through time. Stream flow in this conceptualization is really the master variable that limits the abundance and the distribution of riverine biota. And they focused on 5 characteristics of stream flow that were particularly important. So magnitude, frequency, duration, the timing in terms of season of the year, and the rate at which stream flow changes. A few years later, or many years later, a group of us had a paper in the same journal saying, well, actually, sediment is equally important, and this was mostly geomorphologists, but some ecologists on the team of co-authors. And we said water and sediment that comes into the river systems are equally fundamental drivers of river conditions. You can't move sediment without water, but you don't have a river system if you don't have sediment. You may, unless it's a bedrock canyon, but even those have some sediment. So if you're going to effectively manage a river corridor, you have to understand both water and sediment interactions. And we went into detail in the paper about the details of what aspects of sediment dynamics are important, things like the inputs, the transport, and the storage of that material. And the details of sediment dynamics really interact with water to govern characteristics like the form of the river corridor, its stability, the abundance of habitat, the availability of nutrients, and the disturbance regime. And then finally, just a couple of years ago, a group of us said, well, actually, one more thing. In forested catchments, large wood is very important in shaping river process and form. And of the three, water, sediment, and large wood is the one that people are least likely to think of, because we as humans have such a long history of removing wood from forests with deforestation, but also from rivers and floodplains. But if you look at natural unmanaged river corridors, wood is a little less important in tropical environments like parts of Colombia, but even in tropical environments, wood can play a very important role in influencing river process and form. So we think of water, sediment, and wood, I think of these as the tripod of physical inputs that really supports river process and form, as illustrated in this slide. And finally, I just want to emphasize that I think it's important to think of river corridors not just as physical entities, but as ecosystems that support biota, including us. So the characteristics of that ecosystem, there are multiple drivers, always water and sediment, and in some cases large wood. The river corridor integrates inputs from everything upstream, but also from areas outside the basin. If you think about precipitation, for example, or windblown materials that can come, well, in the case of the Western Americas, it can come all the way across the Pacific, or you can have dust moving in the atmosphere from Northern Africa up to the United Kingdom, for example. There are interactions among physical, chemical, and biotic components. So whatever your particular disciplinary specialty, if you are an earth scientist or an engineer, you can't forget about the chemistry or the biota. That's often what drives management. And because it's an ecosystem, it can also provide ecosystem services that people value and need, such as flood control, drinking water, fisheries as examples. And finally, again, there is that three-dimensional hydrologic connectivity. There's longitudinal at the surface, lateral at the surface between the channel and floodplain and with adjacent uplands, and then the vertical in the subsurface. Okay, so turning to connectivity. Just a very basic definition, it's the transfer of matter or energy between landscape compartments, and you can compartmentalize a landscape as you choose. So in the inset photo here, one compartment could be the hill slopes, the river corridor could be a compartment, or you could subdivide the river corridor into channel and floodplain. But you can have connectivity between those hill slopes and the river corridor via physical contact. You can see this is a photo from New Zealand. There's very coarse sediment coming directly off the slopes into the river corridor. You can also have connectivity even between physically separated compartments. Alien dust, I mentioned that a few moments ago. That can come from well outside the river basin, but if you have a transporting current with enough strength, in this case air, you can bring things across physical distances. And of course the idea of connectivity implies the inverse, that you can have disconnectivity. So this can result from any process or structure that limits physical contact or transfer. So if it's hydrologic connectivity that you're talking about, a lack of water could create disconnectivity. Maybe you haven't had sufficient rainfall to create perennial flow in a stream in the desert. Or it could be a physical barrier. If you look at this photo, there are some alluvial fans at the base of these slopes. So those are temporary sources, or they're sources of temporary disconnectivity for sediment coming off the hill slopes. It may be in residence in the alluvial fan for hundreds to thousands of years before it gets into the river corridor. So whatever degree of connectivity or disconnectivity you have can be applied to organisms, to movement of anything, organisms or materials within the river network. For riverine, hydrologic is of course the whole hydrologic cycle, so precipitation, infiltration, movement on uplands as well as in rivers, sediment connectivity, landscape connectivity. There are a lot of different kinds of connectivity that people talk about in the literature. But for any of these, you can attempt to specify characteristics like the magnitude, how much of the material or organism is moving, duration, how long is that movement occurring, how frequently does that movement occur if it's not continuous, and over what spatial extent is there connectivity or disconnectivity. And just a schematic representation of this, it's a nice illustration from Brierley and Fryer's book on river management. You have different forms of connectivity in different environments, quite apart from anything humans do. So headwaters, for example, they're the source zone, the slopes and channels are closely coupled, the tributaries and the main stem, and sediment moves downstream fairly quickly. As you get to the mid-catchment in the middle of this diagram, it's more of a transfer zone. The river corridor is a little more disconnected from the adjacent uplands, and the channel is particularly disconnected by the presence of the floodplain. The floodplain is much more likely to be longitudinally continuous. You have better channel floodplain connectivity. There's often more alluvium underlying the river corridor, so you have more vertical connectivity. And then as you get into the depositional zone of the lowlands, you have even better floodplain development, a lot of channel floodplain connectivity and vertical connectivity with the hyporheic zone. But the longitudinal sediment transfer is not necessarily very efficient. You have a lot of storage in the floodplains. So there are these consistent downstream changes in connectivity. If you can read sideways, over on the left there, the increasing sediment storage and residence time as you go downstream, less slope and channel connectivity, more channel floodplain connectivity, and again, more of that vertical connectivity with the hyporheic zone. How do we know this? How is connectivity measured? Well, there are a variety of different approaches you can use. You can, of course, take direct measurements of material moving, so ground sensors and different types of measurements. You can measure it indirectly using something like a drone. It's essentially real time, but you can do this repeat measurements through time or over larger time and space scales, space-based remote sensing. You can infer it indirectly. You could take sediment cores and determine the age of the sediment for how long it's been there, for example, and infer something about storage and residence time. And all of these can feed into numerical modeling. And numerical modeling is the most widely used of these techniques, but ideally it's calibrated and verified with other types of direct measurements. So, this is very general. It really depends on what it is that you're trying to measure the connectivity of and over what time and space scales, but there are a wide variety of techniques that can be used. But why do we care about this? Well, there are a series of reasons. One is that it can be very hard to predict what happens in a river if you don't have a good understanding of connectivity because of the presence of nonlinear behavior, so feedbacks and emergent behavior. So we'll start here with a scenario where you have cobbles moving down a gravel bed river. Something causes the local deposition that initiates a gravel bar. That then gives rise to a whole series of secondary effects. The gravel bar increases the hyporheic exchange by creating a pressure gradient in the flow. There's been work done on individual gravel bars that also show that you have different microbial communities living in the hyporheic zone that can increase the emissions to the atmosphere of carbon dioxide. So you have a change in both gaseous emissions and organic carbon and hyporheic exchange, increasing vertical connectivity. The gravel bar is, of course, an obstacle to wood moving down the stream if large wood is present, so you collect wood on that bar, and that gives rise to a series of secondary effects where you can form a logjam that can then promote overbank flow, channel avulsion, lateral channel migration, maybe the presence of multiple channels that branch and rejoin. Any logjam on the main channel or secondary channels creates backwater that stores fine sediment and organic matter. You're likely to trap more wood in that jam. So you have this self-reinforcing feedback that's really increasing lateral connectivity. And the logjam is also having a secondary effect where it's creating a pressure gradient and increasing vertical connectivity. So you've got a decrease in longitudinal connectivity. That means some of the sediment is being stored in the channel. You're likely to store more sediment if you've got an obstruction, and to have woody vegetation establishing on that, so you have greater decrease in longitudinal connectivity. So an example of these types of feedbacks that can occur. And again, if you have an understanding of connectivity, you can predict these better. The ability to resist change during disturbance or to recover from disturbance can be strongly influenced by connectivity, can be increased or decreased. This is an example of high lateral and vertical connectivity, a very wet valley bottom that was able to resist a wildfire that burned the uplands in this catchment. And certainly connectivity influences ecosystem services. I've just illustrated a few here: recreation, flood control, drinking water, and our activities tend to change connectivity. Sometimes we increase it, sometimes we decrease it, but being able to understand connectivity, understand how we have altered it, and how those alterations might have reduced ecosystem services gives us a framework for trying to develop management actions that can restore those ecosystem services. So thank you very much.